All right. I'd like to welcome Professor Dick Hertog. He's from the University of Amsterdam. He's had a long line of work on robust optimization. And more recently, he's also been working on a new technique for solving global optimization problems, building on a technique that has been around for maybe 20, 30 years. There were new line of research supported also by his former PhD student on this work. Based on conic programming. But today he will not be talking on that particular topic. Instead, he'll be talking on maybe something that's good for the entire world, right? To think about cleaning up oceans, broadly to be applicable, so easily understandable for most of the audience that we have in the lab. That I think done over.
Thank you very much. Thanks for the invitation to give this presentation. So in fact, 50% of my time I spent more on, let's say, theoretical research and optimization, and 50% more on applications for the social good, for the sustainability goals. So working together with many NGOs, and this is one example. But I can't resist the temptation to show you a little bit about the research institute that we have on analytics for a better world. So here's a very short video on that.
What if analytics could help us solve the big challenges of our time? Get 50% more plastic out of the ocean for the ocean cleanup, or help thousands of farmers reduce the cost of feeding their cattle with a smart feed calculator to improve responses to food crises, enabling us to feed millions more. Or what if we could help more mission-driven organizations with their digital transformation by making working with analytics accessible for organizations with different levels of data maturity? What if we can? We are Analytics for a Better World. We want to unlock the potential of analytics for people who make the world a better place. We are a nonprofit institute and community of leading research and industry data science experts, dedicated to bridging the gap to impact. That's why we turn data science into an impact accelerator for mission-driven organizations worldwide, to enable changemakers to drive greater impact on their goals and do it more effectively. Let's join forces, because together there's a world to win. Analytics for a Better World, accelerating mission-driven impact. Here to help you help.
Hey,
Where's that?
sorry?
Looks like where is that?
Oh, it is. I don't know, to be honest. You would like to go there? Yeah. Okay, so but today is about one of those applications, and that is the work that you did for the ocean cleanup. So the Ocean Cleanup is an organization in the Netherlands that the aim is, in fact, to remove the plastic from the oceans. And so we built, in fact, optimization methodology for them that they are now using to steer the systems. But I will explain that in more detail, of course. So Analytics for a Better World is also collaborating with many researchers. So in this project, we work together with Jean Pofilet and his PhD student, Bai Zong. And this is also the order in the amount of work that was done for this project. So he did most of the work, and then Jean and I did little work. Okay, so talking about the oceans, plastic is really a problem, although it's maybe not what you think. So maybe you've heard about plastic soup. That's the thick layer of soup, or the thick layer of plastic. That's not the case. So that's really an exaggeration, but still it's a problem for the oceans. And in fact, also the nature is helping us, because due to the currents in the ocean, the plastic is more or less collected in 5 hotspots in the world. Mind you, those hotspots are big. For example, the biggest one, it's called GP, Great Pacific Garbage Patch, is 3 times France. And maybe for you, 2 times Texas. So that's in a big area. But again, we're not talking about a thick layer of plastic, but certainly it's a problem. So we would like to get rid of the plastic, because you've seen the pictures that can cause harm to the animal life, for example. Okay, so the plastic waste in the ocean, so 80% is coming from marine pollution. And yeah, the consequence of that is harm to marine life. So there are costs involved. Also, in estimations are that yearly it costs $6 to $19 billion. So that's the aim of the ocean cleanup. First, the mission is to try to avoid that new plastic is coming into the oceans. So they put all kinds of interceptors near the rivers to avoid that plastic is floating into the ocean. But also they would like to clean up the ocean of the existing plastic that is there. So this talk is about, and what we did is about the first one, to clean up the oceans. The CEO is Boyan Slat. It's a very nice story because he already got this idea to do this when he was at school, high school. In the Netherlands, you also have to write kind of a thesis in the last year of high school. And so he wrote already a thesis about this topic and this idea that he had. So after that, he went to university. But after 2 years, I think he dropped out and started this organization. Okay, so later, at the end of my talk, you will also hear statements about this work, what we did here. So it's about removing the plastic from the oceans. If there are questions, please ask me. Yeah? So let's make it lively. It's more boring. Great. So 2 actions. They would like to stop the inflow and clean the legacy. So here you see pictures of the interceptors. That's of course also important to avoid new plastic is coming in. Here you see the interceptors. Some of the interceptors they have built in rivers in this region most of the time, and also here in this region, because those rivers appears to be the main causes for inflow of plastic. Okay.
So that was obtained by some global analysis from satellites to figure out which was the major source.
Yeah, but just measurements at the end.
Just measurements.
Yeah. But we were not involved there. But yeah.
Do you know what happens with the plastic once it is?
Yeah, it's recycled as much as possible. But yeah, some of the plastic is not possible anymore because when it is a long time already in the water, in the ocean, then it is degraded and then it's not, yeah, you can't recycle it. But they try it as much as possible to recycle. Okay, so they're using these type of systems to in fact catch the plastic. So this was in the beginning, the span was 800 meters. And now they already have a span of 1,800 meters. And the aim is to have 2.4 kilometers span. So 2 tugboats. And so then the plastic, and they sail in that direction with a very low speed. Also for the animals to escape. So it's 2 meters high. And then the plastic is finally comes into this, what's called the retention zone. And then when this is full, they empty it by, you'll see it in the next video, they empty it by a crane. So it's putting up and then the plastic comes down. So that's the system that they have. So here you see a small video about.
So Jenny is a 800-meter long floating barrier which we tow through the water. The barrier is 3 meters deep in the water. It's completely open at the bottom, which is important because it allows fish to escape. And it has flotation along the top, which helps it to keep its shape. Those vessels are moving ahead at a very slow speed. It's about 1.5 knots. As we move through the plastic and through the water, then you get a natural flow of water caused by that movement, and the plastic is carried along those 2 barriers, which we call wings, on each side, and it's transported to a central area, and there's a collection area which we call the retention zone in the middle of that U shape. Then we take the plastic from the retention zone, empty it all out onto the deck. We separate it into different materials according to different recycling streams. We package it up and we take it back onto shore, and then we can send it for recycling.
Okay, so this is how it works. So this is currently or the old system 800 meters, but now it's already 1800 meters. That's the retention zone. Capacity is 25 tons, and the speed is a low speed, such that animals can escape. Okay, I already told you that due to the current, the plastic is collected more or less due to the current 5 regions in the world, in the oceans. These are the 5 plastic garbage patches. The biggest one is between the Hawaii Islands and California. It's called GP, Great Pacific Garbage Patch. That's the biggest one. And in fact, what I already told you, it's 3 times France, and the amount of plastic is around 100,000 tons of plastic there. But still, you can do the calculations. Doesn't mean that we have a thick layer of plastic. So that's really nonsense. But still, of course, it's you have to. It's better to remove it. So if you add up the plastic in the other regions, then that is even less than the biggest one. So this is really the biggest one, the Great Pacific. Okay, you've seen already these pictures here. So this is the system. The plastic particles are then collected in the retention zone. So now this is 800 meters, and they are going to this big system, so 2.4, 2.5 kilometers. So really a huge system. And by the way, they also use our optimization to find the right dimensions for example, the retention zone, the capacity. So also for that, it was used to develop, construct the new system. Okay, so there are also questions about fleet operations. There's so many boats that are used there. Also boats for the plastic extraction, for maintenance, for the transport to the harbors. So there are many questions there, but this talk is not about the boats and so on, but it's about following question: can we use optimization to clean up the oceans faster? So the basic problem there is the following. So we have this system, and suppose that we are in that region of the garbage patch. And so the plastic there is not homogeneous, the density. So there are areas where there's no plastic. In other areas, the density is very high. So you would like to be with this system in areas with a high density. And that changes over time, of course, because of waves and currents and so on. They do have an estimate, prediction for that, based on models, physics models, satellite information, and so on. So then the question is, given the predictions for the plastic density in that big region, how should I steer that system such that we catch the maximal amount of plastic? Maybe you remember the Pac-Man game. So it's like a Pac-Man game to in fact catch the maximum amount of plastic. So that's the basic optimization problem. Very simple problem. Yeah.
Is the motion current driven or wind driven? What's just the time scale for things changing?
Yeah, so in fact, we get predictions for every 3 hours. So both are sources for, let's say, changes in the, yeah. But also the waves are very important for us, not only for, let's say, the change in the plastic, but also because of the safety for the boats. If the waves are too high, that will not be there. So we should also take into account in the optimization. And sometimes if, for example, the waves are above 4.5 meters, then it's possible to be there, but then you have to sail against the direction of the waves. So that's the basic optimization problem. And so I would like now to describe how we developed the optimization. The basic ideas are really very simple, but the impact is high. because of this optimization, they can now, in fact, reduce the time by a factor 2 to clean up the ocean. And that's also what the CEO was saying. They save 4 billion. It's predictions, so we have to see. Okay. So the garbage patch, big area, plastic density is not homogeneous. Uh-oh. And a battery has been. Yeah. Okay. So so that's in fact this optimization project. A design an optimization method such that we can steer the system in such a way that we maximize the plastic that we collect during a day or a certain amount of time. And we also have to take into account all kinds of constraints on the weather and other operational conditions. For example, if the waves are too high, then we have to go against the waves. And when the waves are higher than 2.5 meters, then we cannot empty the retention zone because that's too dangerous, because we need a crane. That's then too dangerous. So there are more conditions. This first one is also very important. It's such a big system, it's impossible to move, to have sharp turns. Okay, great. So we need a lot of data for this. Very important data is, of course, the predictions for the plastic density. So that's not what we did, but they, and also many other researchers in the world, they already developed many methods to predict the plastic density based on satellite information, based on physics models. Here you see a visualization of that. So this is part of the ocean, of the Great Pacific Garbage Patch. So we discretized the ocean there, and the colors indicate the amount of plastic. So green means low density, and yellow means high density, and red means very high density. So let's see, tons per 64 square meters, kilometers. So you already see from this, we're not talking about a thick layer. Okay, so this is about the plastic density predictions. Then we need data about the wind speed and also about the wave heights. So, for example, here you see an example for the wave height. So these are, of course, weather predictions that we get every day. And so the idea is we do the optimization for, let's say, 7 days ahead, for 10 days. We send the solution, the route, to the captain for the next day. After 1 day, we do the optimization again for 7 days, 10 days, and we send only the first day to the captain, and so on. So rolling horizon. And that's, of course, to avoid, so if you only optimize for the coming day, then it is too myopic, and you might end up in a region that's not interesting for the days after. So therefore you do it for more days and only communicates the first day. Because also after 1 day you have new information, also about the weather. So you can use that to re-optimize. So here you see the wave heights, days. And in fact, you see sometimes, I think here it becomes yellow. So that's around 8-10 meters. So it's better to not to be there. Sorry. Wow. Yeah, so that is really dangerous. So you have to avoid that, of course. Yeah. And especially in the winter, this is the case. So especially in the winter, it was very difficult for them to do it. So let's say, yeah, by hand. because there's so many restrictions that you have to look at.
Now, I was gonna ask, so you
Yeah.
just operate during the day or can you operate at night also?
What? Oh, the system. Yeah, 24 hours. Yeah.
Why are captains, why are people needed on these ships? Why is this not all automated?
Yeah, so they started with that. So the first idea was to put a system in the ocean and then let the currents do it. But then, then you end up in regions where that's not interesting. There's not much plastic, so and also other technical problems. But that was the first idea they tried. Yeah.
Okay.
Sounds- Go ahead. So it sounds like it's a classic model predictive control.
To optimal control.
Yeah.
Yeah.
Okay.
Yeah. You can see it like that. Yeah. Because I'm optimizer, so I try to find a solution via
You're forgiven.
my tools. Yeah. But I'd like to get your ideas on it also. Okay, so that's about the wave height. So here you see really high waves. Okay, so the way we solve this is the following. So we did is we discretized the ocean. We discretized the time. So the number of hours, 3 hours, 1 hour, doesn't matter. And discretized the ocean. And then in fact, a path is then in fact a collection of, you could say, nodes on this supergraph consisting of nodes for the ocean and the time. Okay, so we discretized the ocean, and then we also discretized the directions because sharp turns are not possible. So here we used 3 directions. Because here we assume that a change in the direction of 45 degrees is the maximum that you can do. And in this example, we have 3.
What scale is this?
Sorry?
How big are your squares?
That is in total 3 kilometers or 1 kilometer, so it depends. So what we did is 1 kilometer.
Oh,
yeah. And so because there is a low speed for the system, it means that it's
Oh, you're
not
800
that
meters,
big.
so you're digitizing it about the resolution of your net.
Yeah.
Okay.
Okay, so it means that what we did is in fact build a graph of that. And so not only in the graph that I will show you here, so not only what we need is the location in the ocean, the time, but also the direction. Because at a certain node, you would like to know at which direction did you arrive, because that determines also the possibilities in which directions you can continue. And so in this graph a node is characterized by location in the ocean, the time, and also the direction. So it's a huge network. And in fact, what we can also do is we can calculate for such a transition, so from node to node, or it could also be directly to another node, we can calculate then what is the expected, predicted plastic that we collect. Because we do know exactly the time, the direction, and also the location and the new location. So we can calculate the amount of plastic that we collect. So that's in fact, depends on the span, of course. So it's the surface that we cover times the plastic density times the weight factor, because we cannot catch all the plastic. We lose some of the plastic. So the weight factor is something like 0.25. So we can then calculate that, all those rewards. And if we do that for all the transitions, then in fact, what we have, so, and we then connect with a dummy node to the end, and then the reward is 0. Then in fact, we are looking for a path from where we started, starting node, and at the end node, such that the reward, the plastic is maximum. So that basically means we have a longest path problem. So not the shortest path problem, the longest path, because we would like to maximize the blasting. Now, in fact, we have a very efficient solver for the shortest path problem. So basically, Dijkstra's method is behind it. I'm proud to say that because that's a Dutch researcher. But that's for shortest path. So this is the longest path. Normally speaking, the longest path is not possible if you have cycles, but of course here there are no cycles. So this is a directed acyclic graph. And that's because of the time. So we cannot go back in time. So therefore we can use basically the same methods, Dijkstra's method, to solve the longest, to find the longest path. And we can also predict how much time that costs, because we can calculate the number of operations that we need, the number of additions, comparisons that you have to do. I have a slide on that later. And then we could already predict that, in fact, the amount of time is less than a few seconds for this.
So you build the path such that no cell with the spatialization can be visited more than once. Yeah.
Very good point. I come to that later. Yeah. But this is the simple, basic, the core of the approach. I think discretization, big network, and then longest path to maximize the plastic.
So if you capture 95% of plastic, that means you've now created a dead cell. Does your model take into account that that cell, which was predicted to be very rich, is now very poor?
Yeah, that comes back to your question. Exactly, it's said that you don't revisit again,
Right.
because it's not that the small what you cover that stays like this in time. It's floating.
Yeah,
so,
that's my question.
but still it is lower density than you predicted because it's.
Do you model that in that lower?
I come to that later because
Okay, great.
Yeah. Although we have a technical solution for that. I did include in detail here, but
Okay.
I will say
I'll believe you.
about it. Yeah. Yes,
So how is the weather?
Yeah.
Conditions?
very good. That's the next slide. Yeah.
There you go. Yeah.
That's the ideal audience.
Yeah.
If they ask questions, that's yeah. Okay, so this is the network. Yeah, so you can calculate what you, and that's why I like so much the longest path method. So I've done hundreds of applications in my life, and as an operational research guy, an optimizer, I have many tools in my toolkit. So always the question, what should I use there? Should we use linear optimization here? So I also presented this to students without a solution and asked them to come with a solution, and they all started with linear optimization. This, I think, is hopeless here. That's also appeared to be true. So what I like so much about modeling problems as a shortest path or a longest path is that you can predict the amount of time that it needs to solve it. Well, for linear optimization, and especially for mixed interlinear optimization, you never know. You have to wait and pray, and more or less. And so, but here you can already calculate it. And so that means that the shortest path is not only used, cannot only be used, let's say, to find the shortest path from A to B. So it's not only included in, for example, Google Maps and car navigation and so on, but also many practical problems you can model as such as a longest path or a shortest path, like this one. Okay, so here, for example, if you take, for example, 7 days ahead, 8 stages a day, so this could say in 3 hours, we have 56 stages. Number of cells in the oceans, 112 times 112, times 8 directions, even less, I think, okay, but let's do this, 100,000 states. So that means that how many additions do we have? Well, we have then in total 56 times 100,000 nodes. Each time we have to do at most 8 additions and comparisons. So that is in total of 45 million additions. And this can be done less than a second. If you use more time stages, you know, it's maybe a few seconds more. Nothing. Okay. Yeah, now your question about, for example, we have the logistic constraint that when the wave height is too high, higher than 4.5 meters, then we should go in the direction of against the wave direction. Now, suppose that the weather predictions are such that in this area of, let's say, location 4.1, just an example, that a time is 4, that the wave height is higher than 4.5 meters. Okay, so let's look at these 4, where this node is then at location associated with location 4.1. So we have one here, and we have another one here. So here in this node, the direction, this node direction is 5. So that's nice because the direction was predicted to be 1, and 5 is against the direction of 1. So that's okay. So it's allowed to be there. So we leave it. This node here, the direction is 6. It's not against the wave direction. So we delete that node. We delete the transitions. So that means we cannot go there. Does that answer your question?
Yes.
Yeah. Okay, and the same, a little bit more difficult for crane operations and so on. You can also model it like this. Okay, so now coming back to, so this is the basic model that we used and to solve it. So very simple, and this leads to, I'll come to it later, to let's say a reduction of 50% and cost 4 billion. That's what expected. But there are more difficult stuff that I don't present here. And that's also what you guys were asking, because if we go back, sometimes we do go back. So I will give you an example. So this is one of the situations and one of the solutions. So here you see the system. You see that it's really trying to go to the yellow regions. And by the way, what they did before was the following. So if the system is here, then they were looking for, let's say, a red area, and they sailed directly to the red one. But here, what we showed is much better just to make a detour and to go with the flow, with the yellow flow, so to speak. So it takes more time maybe to reach the red one, but in the meantime you collect more plastic because you're in higher density regions.
It seems that the density of the density, so to speak, is a good fit to, right? You've got this sort of snaking, natural sort of.
That's what you see here. Yeah.
Yeah.
We also have another example that we showed. I think it's not included here. And then you'll see that there are regions here where there's yellow and red, and he goes into the more green areas. So it seems very not so logical, but the reason was because there's rough weather there. It's not allowed to be there. So.
So can I ask, maybe it's off topic a little bit, but
yeah,
what is the physics behind that garbage or plastic distribution? Why do they form these long? Does the plastic interact with itself, or?
Yeah. Yeah. So in effect, there is some connection there, and to be honest, I don't know exactly, but there's also some Navi-Stokes modeling behind it. And together with, let us say, satellite information to calibrate that. But what's the real reason is, I don't know.
Any structure.
Yeah, it's interesting, the structure's still there, I mean, that garbage has probably been there for months, right? So you'd think it would diffuse, but there's still
No, it's
a lot of structure. Anyway,
Right into the water.
Yeah.
Yeah, well, what's fascinating, that's fascinating. That's it.
Yeah, but I think that's also the reason that anyhow, and that the plastic is collected in those 5 hotspots due to the currents. That's the major reason why it is.
Yeah.
So I think it's not that much that there's interaction between the plastic, but more the structure of the flows. Yeah.
So it looks like fuel costs for the chase ships are not.
Say it again?
Fuel costs for the chasing ships, the other ships. It's not an issue here. Otherwise you'd want to be tight, right?
Yeah, so in fact the speed is constant. Although I can't do that.
What about the collection ship?
Oh, the collection ship. Yeah, but finally, when there's plastic, they have to get it from the boat anyhow. So there's nothing to optimize there. Maybe the location there, it is easier to reach it.
Yeah.
Yeah.
But I think we win much more to do it more efficient like this, because that saves a lot of fuel costs for those 2 tugboats. And that's much more important in that sense. Yeah.
How do the tugboats get refueled over time?
So there's also a fuel. I showed it.
I
A
see.
fuel boat that refuels.
I see.
Yeah.
Because I think if you're going against the wave, you're probably losing fuel much more at a faster rate than the
Yeah.
other way around.
Yeah.
So overall, maybe your
Yeah.
time that you can actually spend will be lower.
Now, that's
unless you
very
have
good,
refueling.
very good point, because that's also if you look at this. So finally, we start here. Where we end up, it's not determined. So there might be routes that are equally good, but ends at different locations. And then as a second criterion, we may look at the fuel consumption. Or how dangerous was it? This route with respect to the other route.
Do you discount the result far in the future because it's more highly uncertain?
No, and that's because we use a rolling horizon. And so in fact, we solve it for the future,
Right.
but we don't implement that solution. We only do it for the first day. So we include the future only to get a stable solution for the first day, not too myopic. And that's the
I
same.
want to think about that a little. Thank you.
Yeah. And that's the same reason also for, let us say, if you go back to a certain region where we already have been, since we are just do it for 1 day, and then next day we take that into account, that we have been there, so we updated the predictions. We can take that into account.
How fast
Because
does plastic diffuse?
Sorry?
How fast does the plastic diffuse away from itself?
You
Really,
mean,
if you swept an area.
Yeah.
And there was no plastic diffusion, that area is empty for the rest of the time.
no, that's not true, because it is
Right, that's my
diffusion.
question.
It's diffusion. And so
How
other
fast does
plastic,
it move back in?
Yeah. Yeah,
What's
a
the
little
scale?
bit, yeah.
To what time scale does it move back in?
Yeah, so are we talk about a little bit, or so it depends, of course. Yeah. But let's say after months.
Half-life. Let's say you got a cell where you completely emptied it, you did a perfect job.
Yeah.
How long before that cell is now back halfway?
Yeah. Okay. Now that could be weeks, months. Even.
Okay, so
Yeah.
it's a very slow process.
It's a slow process, but
Okay.
mind you, it's not a cell in itself that we emptied. It's only, let's say, 2.4 kilometers in the future systems that we empty, almost empty.
But then your space discretization was 1 kilometer, right? So it's almost like a cell. Your space discretization.
Yeah, it depends on the width and what you use as a discretization. Yeah, 3 kilometers or a 1. At the ocean cleanup, they always say 3 is good enough for us.
But presumably you could compare.
But indeed, you are right that if you go to the future system, then it is really, yeah.
Just saying, presumably you could compare your predicted distribution of trash against what turns out to be the actual distribution of trash,
Yeah.
and get an optimal discounting rate for costs in the scrap, right?
Yes. Yeah. So that's in fact, so I think nowadays, the most important thing is how reliable are the predictions?
Yeah.
Because we took it as input, said, okay, let's do that. But then we were really very, how do you call it? We asked them, is it really correct? And then it appears that there is also uncertainty there. Yeah. So therefore, what we are now looking at is, because I'm a robust guy.
Yeah, I was expecting to see scenarios for the future.
Yeah. So what we are looking at now is robust optimization. Because also in this, there might be many almost optimal solutions, and then you might also pick one that's maybe not theoretically the highest value, but it's much more robust than the others, for example. And there also,
So are there any change after removing the plastics? So the condition is changed by removing the plastic.
So you mean if we collected it, then that's emptied, and then you get, let's say, the diffusion again. So the predictions will then change.
Yeah. So means that has been already modeled.
Yes. But the starting point already. So where is the plastic now? How accurate is that? And they have difficulties to give evidence that it is really good enough, to be honest. Yeah. So therefore, also what we do is, oh wait, here's another. I can look at it for hours. I showed my wife.
Yeah, this is more subtle. Yeah.
But she was saying, "Oh, can you?"
It almost looks greedy.
Yeah. Okay. No, maybe I come to that later. Then let's just do slide by slide. So in fact, that is also important here. How do you apply it? And so you can, for example, plan for one day, optimize one day, and then implement for one day, and so on. That's bad, of course, because that's too myopic, because then you end up in maybe a region that is not good for the day after, or you miss an interesting region on the second day or the third day, for example. So you can do plan 7, run 7. That's also not good. So what we did is run 1 and plan 7 in a rolling horizon. It's much better. Okay, good. So here you see some of the results. Simulation based on the prediction. So in the winter and in the summer, typically you see more gain in the winter by using this algorithm, and that's because of the heavy weather conditions that you have there, and the rough weather. So this is the benchmark, so the method that they used. So that means that if you're here, then you look for the nearest red, highest the density, and then you go directly to that region. So that's the benchmark. And so typically you have to compare with plan 7, run 1. So you typically see here 80%. In fact, it's more than this. So this is really a case where this, let's say, in some sense, the worst case. In the summer, and also a big gain. And so, in fact, this is Boyan Slot again, the CEO of the Ocean Cleanup. And he was saying the following.
So what this means is that when we take our current achieved level of performance and we add hotspot hunting to that,
means
we predict it is possible to clear the Great Pacific Garbage Patch in half the time at almost half the cost. So that means 5 years and $4 billion.
I don't dare to say this, but so I'm not sure if this will be. But I'm a mathematician, so I'm always. I first want to see it. Yeah.
What's the efficiency? How many kilograms of fuel did you burn to get 1 kilogram of plastic out of the water?
I don't know by heart, to be honest.
Okay.
Yeah, thank you. Yeah. But there was a lot of criticism on that, or people ask them, because maybe you do more harm than good.
Yeah, that's what I was wondering.
Yeah, and not only for this, but also for, let's say, maybe you harm also animals by doing this. So they've also a lot of literature and evidence they gave that that is not the case. But you know, I'm not an expert. I can't say if this is correct or not. I believe them. Okay. Yeah, I think we already talked about this conclusion. Yeah. So back to the prediction accuracy. So here you see, in fact, 3 predictions. And they look like the same, but there are also big differences. So we took also cases where the differences were the highest, the same for this one. So it is certainly, you have to be careful here. So again, robust optimization is very important here. Moreover, what they are also going to do and already started to do is use other, for example, drones, boat drones, and also flying drones, but also sensors on buoys. Is that the right pronunciation? Buoys. Yeah. Okay, yeah. To collect information about plastic density. But then the question is also, if the boats are in a certain location and we have such a boat drone, where to send the boat drone to collect the maximal amount of information. So we also did some optimization there to do that. Of course, you would like to get the drone in those areas where the prediction models disagree the most. Then you get the maximal, just to get some intuition, then you get the maximum amount of information. But this is still not used, so we're still working on it. How far is this to the time? Oh, there it is. Yeah, 10 flies. Yeah, so here you see one of the results of that optimization for the routes for the boat drone. Okay. So far about the application. If time permits, I want to say more about analytics for the better world. But even more important is if you have questions about this. Yeah.
So can we evaluate the effectiveness or of this model? Like, is there a way to justify like this model, like the goodness of this model? Like, for example, like can we evaluate the optimal solution from this model by comparing the global solution from higher fidelity models? Like, for example, like if we include like fuel consumption for the other boats, for example, and then maybe some model assumptions here might automatically degrade the optimal solution from like higher fidelity models. So is there any way to justify this model foundation?
I think to justify these prediction, you're talking about prediction models, eh?
It's more like
or the optimization model.
Yeah, longest pass.
Okay.
Yeah.
I think for that, so if we take the input, namely the prediction of the plastic density, if that's the truth, then I think there is a full validation for that, because then we can simulate.
But like from the practitioner's perspective, maybe the purpose is to minimize the cost by maximizing the of course the collection of the garbage.
Yeah.
And maybe we can take other like higher fidelity model, but maybe if you use such a model, maybe higher fidelity, but like you take infinite time to solve it.
Okay.
Right? Like,
okay.
you need to make some assumptions to make the problem feasible to solve. I understand, but like and then you got a really good idea to make it the problem solvable. Like, but is there any way to evaluate this model assumptions with respect to higher fidelity model?
And then you're talking about the optimization part. So basically, you're asking how do we know that from an optimization point of view, this is the best way to go? Yeah, yeah. Okay, yeah. So in fact, what we did is also, let's say, very high accuracy in the number of the discretization for the kilometers and the time, and compared with what we did here, no difference, or up to, let's say, 2% or so, and that's nothing because yeah, there is uncertainty also in the inputs. So in that sense, and also for very small problems, we were able to also develop a mixed interlinear optimization model, and also had to solve optimally. And also there was no significant difference. There's no proof that this works. In all cases, it's the case, but just gives evidence. But that's the practice. Yeah. But the major point here is the validation of the prediction model.
I'm just curious.
Yeah.
So microplastic, that
Yeah.
density is correlated with the plastic. Oh,
Yeah. So and that plastic is also deeper than that. So you don't catch it with this system.
yeah, but is there any, analysis to see the correlation between the plastic floating area and the microplastic density?
Yeah. Okay, I don't know it's very hard if that is the case, but I assume that there must be, and I also assume that there is a big correlation there.
No correlation or correlation?
A
big correlation.
Yeah.
Okay.
Yeah. And so that also in the garbage patch there's a lot of micro plastic there.
Yeah.
Yeah.
So if there
But,
any, something filters with that
Yeah.
boat, actually microplastic also.
Yeah, but then the problem is that you also harm animals, I think, fish and so on. Yeah.
Yeah.
Okay. No more questions. So then still 5 minutes to.
Actually, I do have a side question. From what I recall of minesweeping,
Yeah.
World War II,
Yeah.
they didn't run two boats. They ran one boat with
Yeah.
a drogue on the side
Yeah.
and kept the line essentially straight. It seemed like that would work faster. At least you could go faster because you don't have to worry about stuff getting into the bottom. Was that even tested or considered, or is that?
Yeah. So, and those systems are really also to catch the mines or to detect the mines.
Catch.
To catch it
With
really.
cable
Yeah.
cutters.
Okay, yeah. But maybe those mines were they stayed there, so they could really do it like.
Yeah, the diffusion of the mines was zero ideally.
Yeah.
They didn't move once they were laid.
Yeah. So I don't know the answer. I think for sure they have thought about it, because but I haven't thought about it, and yeah. So I don't know the answer to this. Yeah, I'll ask them. What's the time?
Should have.
It's 4 minutes. No, I think they don't do it. Because it's,
Well, let's ask, would you rather move ahead or have another question?
Yeah.
So 1 second is, plenty of time before the next day, and that leaves the other 23 hours, 59 minutes. In what ways would you want to make the model more fine-grained?
Check the predictions.
More fine-grained predictions. Okay.
Predictions to spend time on that, because that's what is most important now. Yeah,
but
because we can fine tune this method and maybe get 1 to 3% in theory more, but I think the inaccuracy in prediction is higher, so you can gain more there.
And then do you mean more focusing on like the robustness or more focusing on making the predictions more accurate?
Making the predictions better. Yeah. For example, by using also drones and so on. To also have a drone. For example, if you know that you're following this route, also in 2 days. Then you already sent a drone there to look whether it's really what we predicted there. If not, recalculate, go another direction. Very pragmatic, but I think it will work. Yeah.
So I'm curious, have you ever seen that? Okay.
Good.
Yeah.
So I was trying to ask you, for the robust optimization approach, like, are you thinking this is the case where you want to robustify with existing mod inputs? Do you think you can consider the edges that you have in your graph as sort of varying weights that will take into account the
Exactly. Yeah.
Yeah. Have you already considered that? Like,
Yeah. So in fact, when you look at this graph, where is it? This graph. So this is the predicted reward. But you can also, based on those models, if you can get some measure for how sure you're about that, the inaccuracy, then you can also look for a robust path through the network. Yeah.
And did you try validating that the simulations? Does that robustness give you some better performance in general or multiple runs?
Yeah, that is still very difficult to do, but that's what we are going to do, indeed. Yeah, and because you know what you collected, so you can compare with that and compare with predictions, and also with about how to validate the robustness. That is, you can only validate the prediction. Maybe you can compare, but then you have to do long history.
Like you would probably become more conservative in your predictions now,
Yeah.
because you're taking robustness into account.
Now, yeah, so because there are many, because we're talking about 100,000 of nodes, there are many solutions that are almost equally good. So that means that just choosing the one that is the most robust, it doesn't cost you anything in that sense.
Yeah.
But I guess fuel.
And that's always the case with robust optimization, also for linear optimization. In practice, often you have multiple optimal solutions. So then you can take the one that is optimal in a nominal sense, but that's also optimal in a robust sense. So that's the same here. So you have multiple optimal solutions, nearly optimal, practically speaking, optimal solutions. And then you can pick that one that has the best performance on the second criterion, namely robustness.
It doesn't seem like it'd be all that much more computation just to marginalize over all possible predictions according to their probability, right? Just choose the best one-day move given all possible future weathers and all possible future diffusions.
But that I think is not a big problem, because the weather predictions nowadays, if you look when I was young and now, it's now really very, very good for 3 days ahead even. And we only communicate the first day.
Yeah, but I mean, the uncertainty about the future distribution of trash that's one of the things you would marginalize over. I mean, it could be a diffusion process, it could be weather driven.
Oh, so, okay, yeah.
All these sources of uncertainty.
Yeah,
But there's so much trash. The density is so high. State in 2 days isn't gonna cost you anything today.
Right.
If it's very sparse, then you might find yourself off in a corner. My question was, have you ever seen like that bad behavior in the optimization solution? So a bad behavior might be a chattering. Sometimes you get chattering with these receiving horizon problems, or you end up off in a corner, right?
Corner of the ocean.
Corner of the ocean, which is very bad place.
No, I think that's what we avoid, because
We fall
off the edge.
Yeah, that's I think because we use a let's say 7 days or 10 days horizon, and so then you avoid that effect. Yeah.
So actually flipping it, how much better is this than just a greedy algorithm?
Now, so that's in fact the comparison with their benchmark.
Their benchmark was.
Yeah, so
okay, that's 1.8.
That's in fact greedy what they did. So look at the nearest high density region and go directly to
Okay,
it.
so there is some structure then.
But do you put some, penalty on getting too far away from the center, so you don't end up off
No.
to the edge?
No.
I guess this patch is so big and you're going so
Yeah.
slow.
But you don't want to wander too far away from the fuel goal.
Yeah, and so basically what we did is we also looked at suppose that we do 1 day planning, 2 days, 3, 4,
Yeah.
5, 6, 7, 10, 15, 20,
Yeah,
and so on, and then you pick
Yeah.
that one for which you see that the first day is stable,
Yeah,
very pragmatic, but that always
yeah,
is useful. Yeah.
it's a very nice application.
Okay, I think it's time. Yeah, we are hungry. Thank you. Yes, there are many other applications. We also did it for the World Food Program optimization, and because of that, they can now feed millions more people. We many more applications. Very nice. That's next time.
It was fun, thank you.
Yeah.